You believe you understand what an atom looks like, don't you? You've encountered the illustrations countless times before. There's a minuscule nucleus positioned at the very center, resembling a tiny sphere. Surrounding it are electrons orbiting in paths similar to how planets circle around our sun. It appears clean, straightforward, remarkably simple to sketch on paper. That particular representation appears in virtually every single textbook you'll ever open. Walk into any science museum anywhere in the world, and you'll spot a physical model dangling from the ceiling somewhere. Those characteristic little spheres mounted on thin metal wires, spinning perpetually in perfectly neat, orderly circular paths. But here's where we encounter a fundamental problem that most people never stop to consider. That comforting picture you've been shown since elementary school, it's completely incorrect. I'm not talking about slightly inaccurate or approximately wrong. I'm not suggesting it's merely close enough for practical purposes. No, this picture is thoroughly, absolutely, fundamentally mistaken in every conceivable way. It's wrong to such a profound degree that it should genuinely make you question and reconsider everything else you assume you learned during your years in school. The atom bears no resemblance whatsoever to a miniature solar system in space. Electrons are absolutely not tiny planetary bodies following predictable orbits. And if you stubbornly attempt to comprehend what's genuinely occurring inside an atom by clinging to that misleading picture, you're inevitably going to fail in your understanding. You're going to become hopelessly confused and frustrated. You'll find yourself asking questions that simply don't have meaningful answers, and here's why. Those questions themselves are fundamentally based on a convenient lie we tell students. So, allow me to explain to you what actually exists inside an atom. And I'm giving you fair warning right now, you're not going to enjoy this explanation. Why? Because what's genuinely present there is so profoundly strange, so utterly contrary to common sense and everyday experience, that your brain is going to actively resist and fight me at every single step along this journey. Let's begin our investigation with the absolute simplest atom in existence, hydrogen. It contains just one proton and one electron. That's the entirety of it. This is the atom that every physics teacher uses when attempting to explain atomic concepts, precisely because it's supposedly simple and straightforward. You naturally imagine the proton sitting stationary in the middle, a compact little sphere perhaps 10 to the minus 15 meters across in diameter, and the single electron is positioned somewhere out there in space, maybe 10 to the minus 10 meters away, presumably orbiting around it in some fashion. First fundamental question: where exactly is the electron located at any given moment? You desperately want to answer, well, it's positioned over there on the left side of the atom right this instant, moving in a circular path. Wrong answer. Completely wrong. The electron is not over there in any definite sense. The electron fundamentally doesn't possess a definite specific position in space. This isn't because our measuring instruments aren't sufficiently precise or sophisticated. It's not because our technology hasn't advanced far enough yet. It's because the electron itself genuinely doesn't have a definite position at all until the precise moment you actually measure it. This isn't merely philosophical speculation or abstract interpretation. This isn't some debatable theory that physicists argue about over coffee. This is precisely what the mathematical equations tell us. This is what carefully controlled experiments confirm repeatedly, over and over and over again, without exception. The electron exists in what we call a superposition state. It's not simply here or there as distinct alternatives, it's simultaneously here and there at the exact same time, existing in multiple different places all at once. The electron is effectively smeared out in what we describe as a cloud of probability surrounding the nucleus. Now you're probably thinking to yourself, okay, fine, I can accept that. It's a cloud of some sort. So you imagine the electron is spread out, rather like butter distributed across a piece of toast, thinly scattered over some region of space. No, I'm afraid that's still fundamentally wrong. The electron is not spread out in space like some diffuse substance. When you actually measure it, the electron always appears as a point particle, a single localized entity. But crucially, before you perform that measurement, it doesn't possess a position at all. What's genuinely spread out through space is the probability of finding it in various different locations. There exists a mathematical function that we call the wave function, and this function tells you precisely where you're likely to discover the electron, if you happen to look for it. In certain regions of space, the wave function has large values, indicating high probability. In other regions, it has small values, indicating low probability. And in some regions, it's exactly zero, meaning you will never ever find the electron there, no matter how many times you look. But here's the part that truly breaks your brain and defies all intuition. Before you actually look and perform a measurement, the electron isn't secretly hiding in one of those high probability locations. It's not concealed over there somewhere, and you simply don't know where. It genuinely doesn't have a location at all. The wave function is the electron. That's all there is to it. There's nothing else underneath or behind it. Now, let's discuss orbits in detail, because this is precisely where the comfortable solar system picture really falls apart completely. You imagine the electron traveling around the nucleus in a nice, neat circular path, going round and round endlessly like a car on a racetrack. Perhaps it's traveling fast, perhaps it's moving slow, but it's definitely moving somewhere with definite velocity. Wrong yet again. First major problem with this picture: if an electron were actually orbiting in that manner, it would necessarily be accelerating. Anything whatsoever moving in a circular path is accelerating constantly, even if its speed remains perfectly constant, because its direction is continuously changing from moment to moment. And here's what we know from basic physics. Accelerating charged particles inevitably radiate energy away. They emit electromagnetic radiation, light. That's fundamental electromagnetism that we can measure and observe. It happens consistently and predictably. So if the electron were genuinely orbiting as we imagine, it would be constantly, continuously losing energy, radiating it away into space as light. And as it steadily loses energy through this radiation, the orbital path would progressively shrink. The electron would spiral inward, moving closer and closer to the nucleus, traveling faster and faster with each passage instant, until finally, crash! It collides directly with the proton and the entire atom collapses into nothing. How long would this catastrophic process take? Go ahead and do the calculation carefully. It takes approximately 10 to the minus 11 seconds. That's 100 trillionths of a single second. Every single atom in the entire universe should collapse essentially instantly. Obviously, that doesn't happen in reality. Atoms are remarkably stable structures. They don't spontaneously collapse. So the electron simply cannot be orbiting in the classical sense we imagine. Okay, you might say, trying to salvage the picture. So perhaps it's not orbiting in a perfect circle. Maybe it's just sitting there completely stationary, held firmly in place by the electrical attraction to the nucleus. Also, fundamentally wrong, and here's why. If the electron was sitting perfectly still and motionless, we would know both its position and its momentum exactly and simultaneously. Position, right there at that specific point. Momentum, precisely zero. And quantum mechanics explicitly states that you absolutely cannot know both of those properties exactly at the same time with perfect precision. That's the famous Heisenberg uncertainty principle, and here's what's crucial to understand. It's not a limitation of our measurement technology. It's not because our instruments aren't good enough. It's a fundamental, intrinsic property of nature itself. If you attempt to pin down the electron's position precisely, its momentum automatically becomes uncertain and fuzzy. If you try to pin down its momentum with precision, its position becomes uncertain and spread out. You simply cannot have both simultaneously. So the electron is definitely not orbiting, and it's definitely not sitting still. What exactly is it doing then? Here's the answer that frustrates everyone. It's not doing anything at all in the sense you understand doing. It just exists. It simply is. It exists as a wave function, a mathematical description of probabilities distributed through space. And that wave function has certain allowed shapes and corresponding energies that are permitted by the laws of physics. We call these permitted shapes orbitals. An orbital is absolutely not a path or trajectory through space. It's not a route the electron follows. It's a region of space where the electron is likely to be found, described completely by the wave function. The simplest possible orbital, the ground state of hydrogen, is spherically symmetric in shape. The probability cloud has its maximum density right at the nucleus itself and gradually falls off as you move farther away. There's no orbit, no defined path, just a fuzzy, diffuse cloud of _7 higher energy orbitals possess stranger, more complex shapes. Some resemble dumbbells or barbells in appearance. Some look like donuts or toruses. Some have multiple distinct lobes protruding in different directions. These aren't physical objects you could hold. They're probability distributions, essentially maps showing where you might find the electron if you happen to look. And here's the part that's really weird and unsettling. The electron doesn't gradually transition smoothly from one orbital to another over time. It doesn't slide slowly and continuously from the ground state to an excited state. Instead, it jumps instantaneously, discontinuously. We call this phenomenon a, quote, 8-1 moment. The electron's wave function exists in the shape of the lower energy orbital. The very next moment, it's in the shape of the higher energy orbital. There's no in-between state, no smooth transition. It doesn't travel through the space separating the two orbitals. It just jumps directly. How does it accomplish this? We genuinely don't know. The mathematics describes it perfectly. The experiments confirm it happens. But there's no mechanism, no explanation for how the electron gets from here to there without passing through the middle region. It just does. Now, let's talk about what the electron actually is at a fundamental level, because this is where things get really disturbing and uncomfortable. You think of the electron as a little ball, a tiny sphere with some mass and some electrical charge. Maybe it's very small, but it's still a thing, a tangible object, a particle. in the traditional sense. Except when we perform careful experiments, we discover that the electron also behaves like a wave. It can interfere with itself in interference patterns. It can diffract around obstacles. It can spread out and recombine, all the characteristic things that waves do. So which is it really, particle or wave? The answer is neither one. The electron is not a particle in the classical sense. It's not a wave in the classical sense either. It's a quantum object, something that doesn't have any classical analogy in our everyday experience. It's something that exhibits particle-like behavior in certain types of experiments and wave-like behavior in other types, but is fundamentally neither one. When you're not looking at it or measuring it, it's described completely by a wave function. That wave function evolves smoothly and continuously over time, spreading out through space, interfering with itself, doing all the things waves characteristically do. But when you actually measure the electron, when you detect it with an instrument, you always find a localized particle, a single dot on a screen, a single click in a detector, never a smeared-out wave distributed across space. The act of measurement collapses the wave function instantaneously. The spread-out probability cloud suddenly, abruptly becomes a definite outcome. Here, not there. One specific spot, perfectly localized. And nobody understands how this happens. Nobody knows what precisely counts as a measurement. Nobody knows where the wave function goes when it collapses. This is called the measurement problem in quantum mechanics, and it's been bothering physicists persistently for nearly a full century now. There are various interpretations attempting to explain it. Many worlds, pilot waves, objective collapse theories, but they're just interpretations. The mathematics works flawlessly. The predictions match experiments with incredible precision. But we don't have a clear, intuitive picture of what's actually happening at a fundamental level. Let's make the situation worse and more complicated. Let's add more electrons to the picture. Helium has 2 electrons. Lithium has 3. Carbon has 6. Iron has 26. These electrons are all orbiting. No, wait, that's wrong terminology, not orbiting. They're all existing simultaneously as wave functions distributed around the nucleus. But here's something crucial to understand. The electrons are identical, absolutely, perfectly, fundamentally identical to one another. There's no way whatsoever to tell them apart. Not because they look the same, not because they're very similar in their properties, because they are the same. Electron number 1 and electron number 2 are not 2 different things that happen to have identical properties. They're the same thing appearing in 2 different places. This fact has profound consequences. If you swap 2 electrons, exchanging their positions, the wave function of the entire system changes sign mathematically. It picks up a negative factor. This isn't a minor detail. This is absolutely fundamental to how matter works. It's called the Pauli exclusion principle. And it's the reason matter is solid. It's the reason you don't fall through the floor beneath your feet. It's the reason atoms have structure and chemistry works the way it does, and life is possible. No 2 electrons can occupy the exact same quantum state simultaneously. If one electron occupies a particular orbital with a particular spin orientation, no other electron can exist in that exact same state. They have to stack up in different states, filling different orbitals, building the hierarchical structure we call the periodic table. Without this rule, all electrons would collapse down into the lowest possible energy state. Every atom would be chemically identical. There would be no complexity, no molecules, no chemistry, no you. But why does this happen? Why does swapping identical particles change the sign of the wave function? We genuinely don't know. It's just the rule we discovered through experiments. The mathematics works. The experiments agree perfectly. But there's no deeper explanation available. Now, let's talk about the nucleus, because you probably think that part is relatively simple and straightforward. Just a bunch of protons and neutrons packed together tightly, right? Little balls stuck to each other. Wrong yet again. Protons and neutrons are not fundamental particles. They're composite particles made of quarks. 3 quarks in each one, up quarks and down quarks held together by the strong nuclear force, which is mediated by particles called gluons. But the quarks don't sit still inside the proton like marbles in a bag. They're quantum fields constantly fluctuating, interacting, continuously exchanging gluons back and forth. The proton doesn't contain 3 quarks the way a bag contains marbles. The proton is a bound state of the quark field, a stable pattern of oscillation in that field. And here's the really strange part that surprises most people. Most of the mass of the proton doesn't actually come from the quarks themselves. Quarks have very little mass. They're nearly massless. Most of the mass comes from the energy of the gluon field holding the quarks together in a bound state. Energy equals mass, according to Einstein's famous equation. So when you ask what's inside a proton, the honest answer is energy, bound field energy, not stuff, not particles in the traditional sense, just energy arranged in a stable pattern. And the protons and neutrons in the nucleus? They're held together by the residual strong force. They're not touching each other. They're not glued together like blocks. They're trapped in a potential well created by the exchange of particles called pions. But pions are also made of quarks and antiquarks. It's quantum fields all the way down, no matter how deep you look. So let's step back and ask the fundamental question again with a fresh perspective. What's really inside an atom? Not particles in the classical sense. Not little balls or spheres, not orbits or trajectories, not stuff you can point to. What's inside an atom is fields, quantum fields. The electron field, the quark field, the gluon field, the electromagnetic field. These fields fill all of space completely. They're everywhere, always present. When we say there's an electron in an atom, what we actually mean is that the electron field has an excitation, a disturbance, localized near the nucleus. The atom is not a thing in the traditional sense. It's a pattern, a stable configuration of field excitations held together by forces that are themselves carried by other field excitations. There are no solid objects at the bottom of reality. There's no ultimate, quote, 10. There's only fields. And the fields are just mathematical objects that assign numbers to every point in space and time, numbers that evolve according to differential equations. These are numbers that sometimes produce localized excitations we call particles. You don't like this answer. I can see it clearly. You want there to be something real and tangible at the bottom, something solid and substantial, something you can point to and say, quote, 11. But there isn't anything like that. There's just mathematics, equations, symmetries, conservation laws, and somehow, miraculously, that abstract mathematics produces the appearance of solid objects, tables, chairs, your body. All of it is patterns in quantum fields held together by forces, stabilized by exclusion principles, flickering in and out of existence trillions of times per second. Here's another thing that's going to bother you deeply. You've probably heard the saying that the atom is mostly empty space. But that's wrong too, in a subtle way, because empty space doesn't mean nothing at all. The quantum fields are still present there. Virtual particles are constantly popping in and out of existence spontaneously. The vacuum is seething with activity at the quantum level, and the electron's wave function fills the entire atomic volume. The electron is there, in the sense that its probability amplitude is non-zero throughout the atom. When you push on a table, you're not actually feeling particles colliding together. You're feeling the electromagnetic repulsion between electron clouds, field configurations resisting overlap, the Pauli exclusion principle preventing electrons from occupying the same state. It feels solid because the forces are strong, but there is no actual contact, no touching in the traditional sense, just fields pushing against fields. Let's talk about size, because this is where your intuition completely and utterly fails you. The nucleus is approximately 100,000 times smaller than the atom as a whole. If you scaled the nucleus up to the size of a marble, the atom would be the size of a large football stadium. But here's the thing that's almost impossible to accept. The electron itself, as far as we can tell from all experiments, has no size whatsoever. It's a point particle. Every experiment we've ever performed has come back with a result consistent with zero size. So you have a point particle with literally no size somehow occupying a volume 10 to the minus 10 meters across. Does that make any sense? No, of course not. It's absurd. But that's what the experiments consistently tell us. Nature doesn't care whether it makes sense to you or fits your intuitions. Now let's make the situation even worse and more confusing. Let's talk about spin. Electrons have a property we call spin. It acts mathematically like angular momentum, like the electron is rotating around an axis. But the electron is not spinning. It can't be spinning in any physical sense because it's a point particle. A mathematical point has no extent whatsoever, so it can't rotate. There's nothing there to spin around. And yet the electron has angular momentum, intrinsic angular momentum that doesn't come from any motion through space. It's just a property the electron possesses, like charge or mass. We call it spin because it has the mathematical properties of angular momentum, but it's not actual physical rotation of anything. This spin is quantized. It comes in discrete units. Spin 1/2. You can measure it along any axis you choose, and you'll always get one of two possible answers, up or down. Never anything in between. But crucially, before you measure it, the spin doesn't have a definite direction. It's in a superposition of both possibilities, and the moment you measure it along one axis, it becomes uncertain along perpendicular axes. Why does it work this way? We don't know. It's just how spin behaves. Nothing in your everyday experience behaves remotely like this. Energy levels in an atom are quantized as well. The electron can only possess certain specific energies. Not any arbitrary energy, but specific, discrete values. Why is this the case? Because the wave function has to fit around the nucleus in a mathematically consistent way. It's similar to a vibrating string. A string can only vibrate at certain specific frequencies, the fundamental frequency and the harmonics. Same principle applies to the electron's wave function. Only certain wavelengths are allowed, and since energy is directly related to wavelength, only certain energies are permitted. When the electron transitions from one energy state to another, it emits or absorbs a photon carrying exactly the energy difference between the two levels. This is why atoms emit light at specific characteristic wavelengths, why hydrogen has its distinctive red line, its blue line. Each line corresponds to a specific jump between energy levels. We can measure these wavelengths to extraordinary precision. We can predict them using quantum mechanics to extraordinary precision. They match to 10, 12, 14 decimal places. The theory works incredibly well, but why are energy levels quantized at all? The mathematics tells us, the experiments confirm it, but there's no deeper reason we can point to. Now let's talk about what happens when you try to look inside the atom directly. You can't use visible light because the wavelength of visible light is bigger than the atom itself. You need something with a shorter wavelength, which means higher energy. But here's the fundamental problem. The moment you use high-energy probes to look at the electron, you inevitably disturb it. You knock it out of its state. You change the very thing you're trying to measure. This isn't a technical limitation that better technology could overcome. It's fundamental to the nature of reality. To see something small, you need short wavelength light. Short wavelength means high energy. High energy means large disturbance. You can't avoid it. The act of measurement necessarily changes the system. There's no such thing as a passive observation at the quantum level. This is why we can't say where the electron is before we measure it. Not because it's hiding somewhere and we just don't know where, but because the property of being in a definite location doesn't exist until we perform a measurement that creates that property. Before measurement, the electron is described by a wave function, a superposition of possibilities. After measurement, the electron is in a definite state. One of those possibilities actualized. The measurement doesn't reveal a pre-existing reality. It creates a definite reality from a fuzzy one. So what's really inside an atom? Not little balls, not orbits, not stuff, not even particles in the way you think of particles. What's inside an atom is a mathematical structure, a wave function, a solution to the Schrödinger equation, a pattern of probability amplitudes that tells you what you'll find if you look, but doesn't describe a definite reality when you're not looking. The atom is a quantum system, and quantum systems don't behave like anything in your everyday experience. They exist in superpositions. They have properties that are fundamentally uncertain. They defy visualization. You can't picture what's inside an atom because there's nothing to picture. The wave function is not a physical wave in ordinary three-dimensional space. It's a function in an abstract mathematical space called Hilbert space. It's a list of complex numbers that encode probabilities. It's information, not substance. And yet, from this abstract mathematical structure, the entire physical world emerges. Chemistry, biology, consciousness. All of it built from patterns in quantum fields governed by equations, following rules that make no intuitive sense but work with astonishing precision. This is what's really inside an atom. Not particles, not stuff, but mathematics, pure, abstract, beautiful, incomprehensible mathematics. And if that doesn't satisfy you, if you still want there to be something more substantial, something solid and real at the bottom of it all, well, I'm sorry to disappoint you, but the universe doesn't care what you want or what makes you comfortable. It is what it is. And what it is turns out to be far stranger than you ever imagined.